parallel universes, that's different than the multiverse hypothesis, right?
There's actually a bunch of them, so we'll go through them. We have a big, huge, glaring problem in physics, and it's called the fine-tuning problem because it starts looking like design. We could, in theory, get up to a very high fraction of relativistic speeds, essentially by dropping nuclear bombs out the back of a ship with a blast blade. So I can blow your mind if you want real quick. There does seem to be a way to send a message to the past.
What's up, guys? Welcome back to the Luke Lockhart Show. Today we have on John Michael Godier. He's a YouTuber with 2 channels with over 700,000 subs combined between the 2 of them. He's been a science communicator for over 8 years on YouTube, and he has a podcast hosting some of the most brilliant science minds of our time. He has 2 science fiction books he's written, with one along the way. And this is definitely my favorite conversation I've had so far on the channel, so I hope you guys enjoy it as much as I did. John, how's it going? How's your day going so far?
Busy. I just finished working on a video recording and audio editing and doing everything that I do.
I want to start out with one kind of series that you do a lot on your channel, which is about the Fermi Paradox. The Fermi Paradox is really interesting. I think I could explain it, but I think you'd do a better job. What I want to know is what it is, and what do you think your favorite solution to the Fermi Paradox is?
Well, the paradox goes back to physicist Enrico Fermi in the 1950s, and they were talking about, it was actually lunch at Los Alamos, and they were talking about the probabilities of alien life, which are actually very, very high. In other words, when you've got 2 billion chances in one galaxy alone, then that's very good odds that there's somebody else out there. And then Fermi simply said, well, then where are they? Because statistically, we should be seeing evidence of them everywhere, and we see nothing. We see only what David Brin called the Great Silence. And to date, no aliens. Why? Now, as far as solutions go, my favorite, I don't have a favorite per se. What I have is one that I suspect is correct, and that it is intelligent life is simply very rare. And that it shouldn't be surprising that we don't see it. And maybe if we look out there, we'll see life everywhere, but it's microbes and plants and things like that with no intelligent life. Because for most of the history of Earth, that's what it was until we show up. And I think that's probably the one that to me makes the most sense. But there are many others, and if I had a favorite, I would pick the really spooky ones. but yeah, that's the one I suspect is probably correct. It's just rare.
And why would intelligent life, besides just being like the case in our planet, intelligent life is pretty rare. Like we are the only,
Yeah.
I guess you could call sentient life with the level of intelligence to at least make spacecraft. Why would that theoretically be so rare on like other planets?
Well, I think that we need a big sampling of terrestrial exoplanets to look at to see what's common and what's not. What I think though is that with us, all of the evolutionary hoops and what led to us had to happen in just such a way for us to be here at all, and it didn't happen before. Dinosaurs never got to this level so far as we know, and as a result, that's 3.8 billion years, and we just show up. We're newcomers. That's a lot of time of nothing, except dinosaurs and fish, and before that microbes, and it was all microbial for like the first 1.8 billion years. The only thing here were the microbes. So it seems to me to be reasonable that we're just rare, and if we go extinct, for example, and Earth just keeps cooking along, it may be billions of years more before something else arises, or maybe never.
Do you think we'll go extinct? I mean, because we have like Elon trying to get us to go to Mars per se, to at least get us multiplanetary, so something specific to Earth wouldn't really be able to kill us. He's also doing Neuralink so that we can kind of integrate with AI so that AI won't be smarter than us. That's at least the goal. Do you think that won't be enough though, and we will eventually get extinct?
I have a two-level view on this. Can we go extinct? Well, yes, but that gets less as time goes on because we're now able to deflect asteroids, which we weren't 20 years ago. Well, now we can. So as long as we know about the asteroid, the dinosaurs can't take us out. The other thing is that a lot of things that we would normally view as an extinction event really aren't. For example, a full-scale nuclear war will end civilization for sure, but there will be people like in the Andaman Islands and all that that are just so remote they won't even know what happened. And so there are not a lot of ways to go extinct in that framework. But they're also unpredictables, you never know. That said, I think Homo sapiens will go extinct within about 100 years because we will uplift and start modifying ourselves to the point that we're no longer natural Homo sapiens and we're a technological something that's can no longer be classed that. And we're close to that already because we have things like hip implant surgeries where people are getting titanium in there, and we are already essentially cyborgs, and we're going to go further and further into that. Well, at what point does a cybernetic human stop being a completely biological human? We're already close to that. So that to me says that maybe Homo sapiens will eventually go extinct. But at the same time, you have to leave that open because there are going to be people that say, no way, I'm not getting no chips or anything like that. So I think it'll probably split into these augments, and naturals type situation. And, hopefully they like each other.
Yeah, would nuclear war, I feel like it would affect like the atmosphere to bring us, from what I've heard, it would bring us to like a nuclear ice age, right? So would that not affect people who are in like remote islands and stuff like that?
It depends. The models on nuclear winter are not very clear because they predicted back in the 1990s during the 1991 Gulf War that we would get a nuclear winter from Iraq setting fire to oil wells as it retreated out of Kuwait. It didn't happen because what they didn't factor in was the fact that it rained. So the rain prevented the nuclear winter, or analog of a nuclear winter. That said, nuclear winter is a very different thing because it deals with things like firestorms in cities and all that. And it's unclear what that could do, but yeah, there is certainly the potential that it could really mess Earth's day up, but not for very long, a year, something like that for the major effect. And there may be enough to survive. I mean, there are people out there that have a year's worth of food on hand. So I don't know that that would actually result in that or not. But one thing is very clear, it would be absolutely horrible, and I hope it doesn't happen.
Yeah, that's for sure. We talked about a little bit earlier about the Fermi paradox, and like we might go extinct before then. But do you think it's possible, or do you think it is like almost near zero for us to go extinct, like as an intelligent species? Technically, we might like be like evolved or turned into something else, but do you think whatever we evolve into will ever go extinct if we become multiplanetary?
I think it becomes much, much harder, and you'd have to want to go extinct if you're inhabiting multiple star systems and planets within them, because you just have so many chances of survival at that point. And as long as those planets are self-sufficient, and yeah, it becomes harder and harder. The more you spread out, the harder it is to go extinct. And with Mars, should Elon be successful in founding a Mars colony, as long as it's completely self-sufficient and doesn't need anything from Earth, then yeah, our chances of extinction drop dramatically. Now you can't rule out the fact, the possibility that, well, if a nuclear war happens here, what if somebody launches one at the Mars colony, launches one there? Um, So you got those types of things that are lurking there. But fundamentally, he's right in that you dramatically increase the chances of human survival just by colonizing Mars. And I'd also say that I personally advocate for this as well is the upper atmosphere of Venus because it's
Mm.
actually more forgiving way up high in the atmosphere. It's more forgiving than all of Mars is. So you can literally tear your spacesuit at that level in Venus's atmosphere and not die immediately. Um, and that's the only other place outside Earth where that happens, where you can tear a spacesuit. Um,
Why would you not die there, but you would die on Mars?
well, it's because the Venusian atmosphere at that level, I think it's roughly 100 kilometers, is the same air pressure as Earth at sea level. So you don't have any air being sucked out of your suit, and you don't have any being pushed in. And as a result, that's very different from Mars because if you do that on Mars, you're going to lose your air very rapidly, and because of the air pressure is so much lower, so it's almost instant death if you do that. Um, you turn into Arnold Schwarzenegger in that movie from years ago on Mars, where but the with Venus you don't have that problem. You do have a problem at Venus that whatever you build has to be floating in that layer. So it would be literally a sky city, like Lando Calrissian. It would be something like that.
Yeah. And then once we get to planets, obviously the next step would probably be going to different star systems, which is really hard because of, first of all, speed of light and also our technology to like get even to the nearest star system. Nearest star system's like 4 light years away. I think
Four
it's 4 light
point,
years away.
yeah, it's 4.6.
Yeah, 4.6 light years away, and we can only travel at a fraction of that speed. What do you think is the best way that we're going to be able to colonize other star systems if we ever get to that point?
Well, time. You're going to need a group of people that don't mind the fact that they're going to die in space and that their children are going to probably spend their entire life in space until, somebody eventually gets to the destination. And those types of things, generational ships, are the most realistic. But I'm skeptical that anybody's going to want to do that because there's,
Mm.
and then potentially once you get there, unless you know everything about that exoplanet, it may not even be suitable and you have to turn around and come home, unless you terraform it. So I don't know that we're close to that. I think we are close to things like sending microprobes to these, nearby star systems, but not anything else at this stage, and maybe never because it may just prove to be just too hard. But at the same time, I can also envision scenarios where look, climbing Mount Everest is hard, yet, and it's often deadly, yet people do it, and they do it because it's there. So maybe there will be a contingent of people that are willing to do this in a generational ship and just go for it.
Are there any ways to fix that generational problem where it takes so long to get there? Like in movies, you're a science fiction writer, so in science fiction movies and stuff like that, they use cryosleep. But we have like there's cryosleep, and then we can also like just because of the universe, you can slow down time with like relativity. Is there any way to harness relativity or something like cryosleep in generational ships?
Yes. With harnessing general relativity just means speed, because if you're going at relativistic speeds, you're going to be at that star system in 5 years, right? Very high relativistic speeds are unrealistic because you don't have the energy, but the 90% is doable. The thing is that what you give up, and it'd only be, like I said, 5 years for you. What you give up is you're traveling into the future as well. So you're going to be some years ahead of where you were. So if you don't care about your past and all your loved ones dying and all that, yeah, you can do that. And that extends much, much further, because if you extend that over a lifetime and you're going at very high relativistic speeds, um, the galaxy is nothing compared to what you can do. You can cross the majority of the observable universe within a lifetime at that speed
Mm.
because of the dilation. Um, so there is that, but you just have to have no connection with your past, because it's going to be long gone and you'll never get back to it. Um, so
And is there a way for us to reach those relativistic speeds with like materials we have? Is there anything with the laws of physics that prevent us from doing that?
nothing at the moment. We could, in theory, get up to a very, very high fraction of relativistic speeds, maybe 10% with current technology, essentially by dropping nuclear bombs out the back of a ship with a blast plate and getting it going that far, that fast. That was actually an idea that Freeman Dyson came up with in the 1960s, was a nuclear bomb powered relativistic spacecraft. And that's possible. Anything else though, it's all energy and what you can do. The other way to do it and get up that high is just do it gradually. Um, and then your big problem once you're up that high is slowing back down. You're going to require a lot of fuel uh,
Mm.
of some sort. Now, with the nuclear bombs, you just flip the spacecraft around and start detonating them in front of you. Um, but that's the main idea that we could do today if we were motivated. I'm not saying we should do that. That would be pretty crazy and expensive, but we could do it. We could do it with current technology.
That would be a way to get rid of all of the nuclear bombs we have on Earth. If
Yeah.
there's like people, we sign a rule that you can't have nukes on Earth, and we're like, we got to use them for something. So just use them to send a spaceship really, really far.
Yeah.
And
Put them to good use, diverting asteroids and sending out starships. Although diverting asteroids with nukes probably isn't going to work, but you just blow the asteroid up and then it's still coming at you. But impactors do work, so we got that. But yeah, you could use Earth's nuclear stockpile. I think you're going to need even more than what we have, though,
mm,
because the world's arsenals, and it's still in the thousands. It's not in the
mhm.
tens of thousands or anything like that.
Yeah, and what I thought was interesting is if you are going, let's say, near relativistic speeds to where it's like it's like 5 years for you. Would you count that? So let's say it's 4 light years away, and you go to where you go like near the speed of light. Let's say like 99 point, let's say like 99.8% the speed of light or something like that. Um, and you reach the 4 light years away. Is that considered? Because like if you were to trace it just on a line, that's like almost the speed of light, so it should reach there in almost 4 years. But who's getting the relativistic effects? Like whose time gets shorter, and what exactly is those 4 years?
Okay, so how it works is relativity, to boil it down, and this is actually something that's not often said, but it's the basis of it. It's all about frames of reference, relative frames of reference. So in one frame of reference, let's say Earth, time is passing at one, rate. And your spacecraft that's flying in that frame of reference, time is passing, um, you know, incongruous to Earth. So if you're on Earth looking at that spacecraft, it's appearing to it's two different perspectives ultimately, and that's
Mm-hmm.
that's the uh the reality of general relativity. But in the end, 4 years for you on your spacecraft is going to feel like 4 years normally in your frame of reference. On Earth, 4 years is also going to feel normal in your frame of reference. They just no longer meet up with each other.
Yeah. And one of the things that is kind of a consequence of that is that if technically faster than light travel was possible, like if we had enough energy, which isn't possible, to get faster than light, it would break causality, which I have watched so much on to try to figure out why it breaks causality. But every time I try to see how it's explained, why faster than light breaks causality, it doesn't seem to make sense to me. Do you have a go-to like explanation for why it does that?
Yes. You have to think of causality as cause and effect. Very very simple.
Yeah.
And when you break causality, you so when you go faster than light, right? You exceed c, the speed of light. The prediction is that time moves backwards, and that's what breaks the causality. And you get all the paradoxes, of the grandfather paradox and all that. But that's not on as solid ground as it used to be, because we don't really know. I mean, things like the many worlds interpretation and stuff like that, where, timelines are splitting off, may preclude that. So there may not actually be a prohibition against time travel. There just may be a prohibition against time traveling within your universe, right?
Mm.
And at the moment you do it, you split another one, and there it's in a different framework. If that model is correct, now there is a lot of disagreement on that one, and how would you even test it? But
So would that explanation be similar to like Avengers Endgame kind of time travel, to where if the many worlds interpretation, the parallel universes interpretation was correct, if you go backwards in time, you don't change the future that you're affecting, you're actually creating a new timeline?
you're changing someone else's future, and you've just joined it, um,
Mm-hmm.
and left your own. But again, in this interpretation, which is very contentious, you know, I mean, it goes to infinity, infinite number of alternate universes, and that, how does that happen? Where does the matter come from? Does it even matter? So you've got all of those questions in there. Now, there are, of course, loopholes, and there are two that are coming to mind right now. One is the Alcubierre drive, where you're not actually violating this; you're just putting spaceship in a broken off piece of space time, and the spaceship itself isn't moving, but the chunk of space is inside the warp bubble, and there you have no restriction on speed, so you can go faster than light with that. The catch is you need a lot of energy. In other words, vaporizing Jupiter levels of energy, and there isn't a clear way to stop it. So once you get it going, you may not be able to stop. So there are all sorts of open questions about the Alcubierre drive metric that are unanswered. Um, and the other thing is that it in itself is also a time machine. So um, you have that. The other is that we don't really understand time itself. We don't know what time is, and you'll get different answers from different physicists as to what it is. Um, as far as a physical phenomenon, is it a dimension as string theory sees it? Is it is it a completely constructed thing, and that humans, so we don't know. But in the context of time and entropy and all that stuff, we don't know what the rules are on certain things, like retrocausality. Can a particle affect its own past? And there's some work that seems to say that yes, a subatomic particle can affect its own past, and that would explain spooky action at a distance, and that sort of thing. Probably can't do that with an object, but a subatomic particle might be able to redefine its own past.
Mm-hmm. And spooky action at a distance is where like two particles are connected. It can be in any parts of the universe, and they will be the same when you measure them.
Right.
And one thing is that I think Einstein thought was, or maybe someone else, that it is predetermined, but uh, scientists don't seem to think that it's predetermined. How do we know if it's predetermined versus if it's not predetermined?
Yeah, that's been a big debate in that it was predetermined, but a lot of people have thought, like I said, with retrocausality, they've thought of ways that it doesn't have to be and that it's not predetermined. And what happens is the particle, when the two particles are entangled at a distance, when one changes state, the other instantly reacts. Okay. Well, that could be through some connection to another upper dimension that they're not separated, in that dimension. Or it could be that the particle, when it changes state, it messages back to the moment they became entangled in the first place, and that forces it on the other one. So it's determined by the state change referencing and informing the past, which lets the other particle know. As weird as that is, but it gets into things, nebulous things, like probabilities and all that sort of stuff. And, you know, we know of all kinds of weird stuff. Heisenberg's uncertainty principle, smearing, quantum tunneling, that all just don't make sense in our big world here. But yet they exist. And, I mean, our computers right now are working on quantum tunneling. It happens.
Yeah, how do you? I've heard that you can't really influence the like connection between the two particles to actually send a message
Right.
between the two. Is there anything in physics that prevents us from ever figuring out how to do that, or is it we just haven't figured out how to do that yet?
So it depends. All right. The big vexing problem with spooky action at a distance and things related to it. The the big problem is that the information is useless. It's not predictable. In other words, you can't decode anything. So it doesn't appear right now that the universe lets you do it. Is there something hidden in there, new physics that we don't know that might? We have no idea because we have an incomplete view of physics. Um, However, if the retrocausality thing is right, there does seem to be a way to send a message to the past hidden in that,
Hmm.
just on its face. And that might actually prohibit it from ever having legs because, again, you violate causality by messaging the past.
Yeah, and the we talked about the parallel universes, and from what I understand, that's different than the multiverse hypothesis, right? The parallel universe and the multiverse hypothesis are two completely different ideas.
Yes. Um, there is there's actually a bunch of them. So we'll go through them. The first one is many worlds where, everything is quantum timelines are all, even down to the quantum level, are all splitting off from each other constantly, which means there are, almost infinite amount of parallel universes, existing within the same space, right? That's the first one. The second one is the
How,
multiverse.
how would they inhabit the same space? Like it would they like in the Flash they vibrate at different frequencies, but is it do they
Yeah.
physically inhabit the same space?
The only way you can say it is, yeah, they're vibrating at different frequencies, but um, we don't know. You know, we have no idea. Um, the others, another one would be the multiverse in the sense that our universe is one universe, and that outside of it there are others, and it's like bubbles, in a bath. It's they're all over the place, and there's that. Another interpretation is that new universes splinter off from this one, meaning you go through a black hole and you end up in another universe. That's a third way. And then there is the ideas of membranes, M theory, where it's, each universe is like a membrane, and sometimes they hit or something hits, brains hit, and then a universe shows up, like sheets on a clothing line. And then there is,
And
yeah,
the bubble universes are those like bubbles because they're visible universes just like the light we can see, the planets and everything around us? Or is that like physical universes, like outside of those universes and in between the different universes is like nothing, like no space time, just like they're just separated?
We don't know. We don't know what they would be like because we have a big, 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 huge, glaring problem in physics, and it's called the fine-tuning problem. In that this universe, about 100 different parameters had to come be set just so, in order for us to be here, right? And if you mess with any of them, and some of them are very, very weighty as far as what happens if you mess with it. For example, change even slightly one of them, atoms can't exist. In other words, this would be a universe that would be nothing but quarks and things like that.
Mm.
And it gets deeper and deeper. For example, the universe is remarkably homogeneous. In other words, its temperature is very, very even. When you look at the cosmic microwave background radiation, you see variations in temperature, but it's very, very, very tiny. It's possible that had those tiny variations not existed, the universe would forever be a lattice of hydrogen atoms and nothing would ever clump. So we don't know. When we talk about these multiverse universes, their rules may be different and they may have no matter at all. They may have a different number on gravity, how powerful gravity is. And in which case you could have these universes collapse on themselves and turn into black holes. There's just any number of things, so they could all be different. The problem is with that idea of the multiverse is that it is only invoked because there's no evidence for it, although some people have thought of potential ways to test it, to look for universes colliding with each other. But it's only really invoked because of the fine-tuning problem. Because if you've got, a trillion other universes out there and, they don't all line up with their parameters, they're not all habitable, very few of them are, then that solves the fine-tuning problem because you just won the lottery and you're in the universe that allows it. But that's the only reason. Otherwise, the fine-tuning problem, they get uncomfortable with it because it starts looking like, a design, which I don't personally have a problem with that, but that's really the only reason that one's, invoked.
Have you looked a lot into the question of God's existence? Because that the fine tuning problem is probably the biggest thing for me. All the different constants being so extremely specific.
Yeah.
But it also, the existence of a God seems to be able to explain a lot of things like morality, humans existing, ethics, and objective reality. And it seems to explain a lot of things. What's been your experience with that question of God's existence?
I, of course, have went through all of that. I started out as a kid, raised religious and all of that, Christian. And, well, over thinking about it over life, I am no closer to an answer than I was when I was 5. All I can say is that I'm open. I, I don't know everything. I don't, I don't prescribe to any organized religion, but I view God, the possibility of it, as something like Einstein did. The God of Spinoza, just a very distant, something prime mover that maybe they set something, in motion, or maybe not, you know. So I just leave the question open because as a human, I just simply don't know the answer to the question.
Hmm. And for me, it's a huge question because there's so many people that believe in a God that will either send you to hell for eternity or send you to heaven for eternity. And for me, it's just like I got to make sure I'm right, because if I'm wrong, that is terrible and that has literal eternal consequences for me. So, for me, this podcast is one of that's one of the reasons I'm doing this podcast, is because, like, it's getting more people's perspectives on where they've come on that question and how they've approached it. Has your kind of exploration of physics given you any insight or given you any thoughts on like maybe that it's less likely that God exists or it's more likely that God exists, besides like the fine tuning?
I think that if, other than the fine tuning problem, which as we know, there are ways out of that with the multiverse, it's possible also that there's no other way it can be. In other words, the parameters are there because nothing else is possible. So you got that. Beyond that, I see no evidence of any intervention of a God. Now, other people will disagree with me, but I just see no evidence for it. And my default is, again, and I'll quote Carl Sagan, is that faith is belief in the absence of evidence by definition. And that's fine for a lot of people, but for me, I withhold belief without evidence. And my leading me in that, in science, led me to say, again, it's, if there is one, it's not intervening unless it is doing it, personally. Everybody's experience is different. Some people say, yeah, God intervened. Well, there you go. But that's, specific to you, right? And I can say certain things. How did I end up, with an enormous YouTube channel, talking about aliens? How did I do that? Well, was that, but I can't, again, my rational side, science brain just doesn't let me go that far. And then there's options other than that, like simulation theory and Boltzmann brains and all those sorts of things that could result in it as well. What I don't do is try to put a definition on it through an organized religion, because there's just too many humans involved in that. And I don't believe a word anybody says that they know. Whenever someone says, I know more about God than you do, I don't believe them. I don't think that any of us know, and I don't think we're supposed to know. If there is one, it did everything possible to conceal itself. And there you go.
Yeah. I think it's really interesting to see how we don't really we don't see God is real written on the sky. I'm not really sure the philosophical implications of that. If God was like, I don't want people to, my creation is enough for people to believe in God, and me just writing God is real on the top is just like a constant reminder that I'm kind of like a helicopter parent. I'm not sure I love that explanation. But the faith versus reason is an interesting one, because I have a lot of friends who take that version of faith, that what you just said, the faith is belief in the absence of evidence, and they take that full force. They will say, oh, why do I need to justify this? It's just what I believe, and I believe I'm right. And I think for me, I like the definition of faith a little bit better, which is what we all have. We constantly have a version of faith where there is evidence, but there's still that leap there where you're trusting a person when you never really know what that person's going to do. Like if you're driving down a highway and you see another person coming towards you, you have faith that they're not going to swerve and hit you head on. And my version of faith is that the deity, the God that created the universe, would be a belief that he isn't lying. And when he revealed himself, he is being trustworthy and actually loves me or loves everybody here. I like that definition of faith a little bit more, but I don't know. Some people don't really love that.
Well, you're going to have all different views in religion, because it doesn't really work like science. Science works on what is, fact. But when you're dealing with spirituality, it's more about what's in here, right? For each individual person. And I actually consider it a very personal, thing, a faith-based belief system, and that arguing about it is frivolous because if there is a God, then it's between you and God, and what other people say doesn't matter.
Hmm.
Just go with your heart.
Yeah, and you were talking about different types of universes. I think you got to like a fourth one. Were there any more that you were thinking of?
Oh yeah, there's a couple more. There was so one would be an idea of two universes. Okay, so we don't have an explanation for gravity. We don't really know why gravity is the way it is. It's a complete mystery. We don't have a quantum theory for it. We just don't know. We just know how it acts. Well, where is that gravity coming from, and why is it so weak? Why is it so incredibly weak compared to the other forces of nature? And one idea is that it's because gravity is leaking into this universe from another one that is hovering just above us. And that was one idea that was floated. And then the other one is what what exactly is dark matter? You know, is there another universe made of dark matter, a dark periodic table, dark aliens, all existing in the same space we are, but not interacting? Um, and that's the one that has the most evidence because we definitely see the hand of dark matter everywhere. We just don't know what it is. So those would be the main types of having alternate universes.
Yeah, and the alternate universes is interesting because I think one of them I heard was the idea of like an infinite universe. Like, there's so many different explanations or kind of theories about our universe that maybe it's like a donut or it's just like a sphere shape. So if you go in one direction, you end up coming up back at the same spot you started at. But one of them is that it's an infinite universe, which I would take when was thinking of an infinite universe, I would take as space time is infinite, but the actual matter, there's like a certain point to where, like, at the Big Bang, matter exploded and we are like, it's only gotten to a certain amount, but
Unanswered
like,
question. Unanswered question. Was there space here before the Big Bang? We don't know. The other thing is that the Big Bang was such that it doesn't really define itself as, you know, it doesn't really define itself as finite or infinite. There's nothing about it that gives you the answer. So you wonder about it. But there is a hint that, okay, in an infinite universe, the geometry of the universe, for lack of a better term, would be flat. In other words, it doesn't curve. It's not a torus. It's a flat. That was recently demonstrated experimentally. So the universe very well could be infinite, and it never curves back on itself. In which case, there's your answer to alien life because there's an infinity. It's everywhere. You know,
hmm,
you just have to go far enough. You would even find almost exact copies of yourself if you went far enough, and it
yeah.
because of the implications of infinity. Um, that said, does the matter extend all that way? Nobody really knows.
Why would the matter extend to infinity? Why would there be an infinite amount of matter?
Unclear. Um, there, you see, that's a problem with it because if you have an infinite amount of matter, that means infinite energy, and that's a really hard one to buy. That you know, a universe would result in infinite energy. How? You know, instead, it appears to say that there's a finite amount, and that, you get what you get. And matter is just simply condensed energy, basically. And I think that stands in the way of that. But these are just these ideas that we have, these crazy ideas. These are the scientists spitballing. They don't know yet. It's just we could look down this avenue, we could look down this avenue. This might make sense. And none of them are proven. And there's a lot of work to be done on a lot of them that we haven't done yet that will indicate whether they're true or not. And then there is the unknowables, things that we can't ever know, which may be the case within science.
Have you come up with any in your time doing science fiction writing? Have you come up with any fun theories based off of physics that you know?
Fun theories? Not really. Um, what I tend to theorize about is biology, right? And there I have, floated a few things. And that's because my fascination with space is equaled by my fascination with the question of how did life arise here? What exactly were the circumstances of abiogenesis? And is that common or is that very rare? Because that answers the Fermi paradox. If that chemistry that happens is unbelievably rare, then it's a dead universe, mostly.
Mm.
But if it's common and some scientist puts all of the ingredients together and pops a microbe from the test tube, then life is everywhere, right? And then you get into what we started with was the intelligence question. Okay, microbes are everywhere, but what about thinking brains that can build starships? Um, so that's a one of life's biggest questions for me is what exactly happened that caused abiogenesis? What was the process? Thankfully, I think this is one question that will be answered within my lifetime because we're close and there are already indicators, findings that show that abiogenesis might be a lot easier than we thought and that we were actually overcooking the turkey and that it's simpler than we thought it was. Case in point, RNA. It used to be thought that there were all kinds of ideas on just how exactly RNA came about. That people were talking about radioactive beaches, when Earth had more uranium and things like that causing it. Um, and it turned out all RNA was a chemical process that happens in a volcanic glass as water and nutrients percolate through it. And then it's been experimentally shown out pops junk RNA. It was that simple. Hot springs and volcanic glasses. So
Have we seen RNA like pop up naturally besides engineering it in a lab?
no, but we haven't looked for it. Um, we haven't yet looked. So the next part of that experiment is to go out to the suitable hot springs and see if there's anything there. Um, but it could be that RNA is popping up all the time. The thing is, the RNA is going to need to hit the lottery because it's just gobbledygook. It's not a code of anything. It's just gobbledygook, and every trillion molecules of this stuff, there might be something useful that gets you closer and closer to a microbial life. But there's still a lot of unanswered questions. But it there's two ways to answer it. There's that scientific way in the laboratory, or you go out, you drill into Europa and find microbes there, and they're not related to us. No, genetically not the same. That tells you right there the same. It's a double whammy. You could answer it either way.
And how close is, like, let's say we find out that there is RNA just at those hot springs. We go and find some just random RNA, no like good code in there at all. How close with good code is that to like forming microbes once we have good RNA?
Well, it depends, because you don't really know. We know what our brand of microbial life did, but who's to say there's not other ways for that to happen in different configurations? We don't know. It's all hypothetical. Um, so we don't really know yet. But I think that again, with genetic research the way it is, we're gonna know. Won't be long. So I think that's the defining factor. Now I just remembered something. So you initially asked about generational ships and what could be a game changer, and there is one, a huge one. It extended the human lifespan. If you
Mm.
live 10,000 years, then a 100-year trip to another star system is nothing. Just a small fraction of your life. Enjoy it. It's like going on a cruise for a week, but just a lot longer. But that to you, living that long isn't that much of a fraction of your life. So people might find it worthwhile if we ever get there. Um, but that said, that's only life extension, and eventually, you're going to have an accident. you're going to get vaporized or something the longer you live. So nothing is forever, but you can extend life. And it looks like we're going to make some inroads in being able to do that um, in the coming decades.
And if we couldn't cryo freeze like a person, if we did extend their life, we could just like put them in an induced coma, right? Like just an induced coma until they got there.
The problem with cryogenic freezing, and this is a big one, is that you have radioactive isotopes in your body naturally. And if you're frozen, within a certain amount of time, you will accumulate a dose of radiation that's fatal and unrecoverable just from the radioactive active isotopes present in your bones. So whatever you do with cryogenic freezing is going to have to be backed up with nanotechnology, molecular nanotechnology that can actually repair cells. We're not anywhere close to that yet. But once you got that, then yes, you could put somebody in cryosleep that's being maintained by nanotechnology in their blood that's repairing all that DNA and damage that the radioactive elements are inducing on the body. That's the only way you can do it. But if you look at the people that are freezing people now, Alcor and all that, they also are saying the same thing. They're saying, no, we can't wake anybody up until we have that nanotechnology because it's
Mm.
going to have to repair all of these cells that are, getting damaged in the body. And the early people that are frozen were, I mean, they're so damaged, because ice is sharp and it just destroys cells. So those early people in the 1960s that were frozen that are still around are going to need a whole lot of work if we ever can get nanotechnology like this to work on that level. And then with later people, they do a process called vitrification. And that one is a lot more forgiving. So people that are getting frozen now have a better chance, but they're still going to require a whole lot. And my question is a person when they die, is consciousness like a standing wave? And once it's gone, it's gone. And that when you wake that person up, you get the Frankenstein syndrome where it's not the same person, you know? Um,
Yeah.
and that's actually where I can give you a religious statement. I would never do that. I'll extend life, sure, but I am not getting frozen because I want to see what comes afterwards, you know?
Yeah.
And let's see what happens.
And I think that's a pretty similar problem that we have with teleportation. If you want to teleport somebody, like you break down
Yeah.
them down to an atomic level and then reconfigure them at the atomic level, are they the same
Is
person
it
or
the
are you
same?
just Frankensteining
Is
that?
it the same person? And I would be skeptical that it would be. Um, and I would also say that about, if we ever get to the point with Neuralink and those types of things where you can actually upload yourself into a computer, are you
Mm,
uploading a copy? Yes, that's not you. Where
yeah.
I think you can do it though is that if you went and gradually replaced somebody's neurons, brain cells, cell by cell over a very long period of time with artificial cells that contain that information, then you could become cybernetic or a complete, you know, robot version of yourself and still remain you as far as from your
Hmm.
perspective.
Have you heard of the ship of Theseus?
I have, yes.
Is that pretty similar thing if you replace all the specific neurons um, with like cybernetic replacements and then eventually you take all those neurons that you replaced, make them back into let's say a brain or something like that? Which one is the actual person?
Well, the ship of Theseus ends up as no longer the ship of Theseus because it's been entirely replaced. And yes, that effect works for a human as well, but you have to remember we're doing that anyway now. I'm not, my brain cells, neurons are original, but every other cell, has been replaced multiple times over life. So you're not the same person that you were 20 years ago. And that's so you're doing it. You are already in the Thesean ship scenario other than very permanent things like neurons. That said, with stem cells and all that sort of thing, again, we don't know, does that change you? We don't know.
Well, the video is not sponsored, but any YouTuber you put down in the comments, I will personally look at their channel and see about getting them onto a future episode of the podcast. So don't miss out on that. And this channel also has to get to 1,000 subscribers to get this channel monetized and so that I can get money from YouTube. So if you want to help me out in that way, I'd appreciate that. And it'll also help you not miss out on any future episodes with like a YouTuber that you might enjoy listening to.
So I can blow your mind if you want real quick.
Go right ahead.
So you mentioned the idea of the creator, the painter signing the painting regarding God. Actually, we have two candidates where that might be the case in science.
Really?
Yep. One of them is solar eclipses. What are the statistical chances of a civilization appearing right at the exact time of perfect total solar eclipses being possible on Earth? Because they were not possible all that long ago, and they won't be possible in the future. They will never be exactly the same size. So what are the chances of that? And obviously solar eclipses scared the bejesus out of ancient peoples. They thought that they were something, religious or whatever. And so is that a signature? Well, it's up to you. The other one is called the axis of evil problem, and that if you look at the universe on different scales, right? One of them doesn't add up, and it seems to suggest that the Copernican principle is wrong, and that our position in the universe is privileged somehow, and that it brings back Aristotle all of a sudden, that the only way we would see that is if we were literally the center of the universe. There are candidates for that really made the scientists go, whoa, how is that possible? And there's other ones. The axis of evil in that framework, by the way, shows the solar system's plane where the planets are orbiting exactly aligns in a certain way that says that, with the rest of the universe, that suggests that. And that one that's unexplained still. We don't know what that is.
So what does it suggest? Does it suggest that we are like physically the center of the universe, or what seems to suggest that breaks the Copernican principle?
What happens is the universe at that level, right? And there's multiple ones, and you don't see this anywhere else. You just see it in this one level. That the universe looks different above the plane of the solar system than it does below it. So that suggests that the plane of the solar system is aligned exactly to the universe, which it's not a lot of chance for that. So if that measurement is correct, you always have to ask the question, is the observation correct? And if you redo it, do you see the same thing? But if that's correct, then that's awfully weird, because that seems to suggest that that there is something special about this point. But that doesn't, they're just oddities, and they could simply be flukes. And that there are so many possible flukes that, you just got a couple of them.
Are we aligned with the visible universe, or are we aligned what we think the universe outside the visible universe is?
Well, we don't know anything about outside. We just know that there's more to it than what we can see. But we don't know what the alignment there would be. It's just assumed. So homogeneity is assumed. So the universe looks more or less the same any direction you look. And they think that there's no reason to think that it would be any different outside of the visible universe. But we don't actually know that,
So if it is aligned, is that aligned in like, let's say like a plate where let's say we put like a really big plate on top of the universe, like maybe to split the universe in half, and that intersected with the center of the universe,
right?
We would be like in the plate? Is that what we're saying?
Yeah, we would be in the plate, and that we see things slightly differently above it and slightly differently below it. And that
Mm.
is the axis of evil problem. That said, though, it's only in one context, and there are other contexts where you don't see that at all. But in that one context, and it's just sort of it's an oddity, you know. But either one of those could represent something, you know, signing the painter signing the painting. We don't know, and they're both completely within science. They're observational. I mean, they're clearly there. You can walk out and see the solar eclipse. Um, so, as a matter of fact, I did that not long ago. So
Yeah, that's
yeah,
cool.
yeah.
One thing I wanted to run by you, I think I've been thinking about this for a little while, is the concept of energy. It seems to have a bunch of different forms, like electrical. I mean, now we have like dark energy and all these different kinds of energy. But it seems when you look closer at different energies that they're all just like kinetic energy, like the smallest form, or potential energy, maybe within just like atoms or matter itself. Would that make sense that all energy is just kinetic energy, like heat is just the kinetic energy of the small atoms moving around?
I think that kinetic energy is a big, yeah, it is, except quantum effects. When you get down on that level, it looks different, you know, in the quantum scale. And an example would be, for example, um, this is fresh in my mind because I'm releasing a video on it later. That, okay, when you get it to its lowest state, it's absolute zero, right? 0 Kelvin. And that's where all kinetic energy stops. You know, it's just atoms are sitting there, and it's their vibrational energy. They're just sitting there as still as they can. But they're never completely still because quantum effects are still moving them around, you know? And then we actually found a way to go below 0 Kelvin in a certain experiment that shows that you can actually calm them down even more by manipulating the quantum states to make them even less energetic. And the strange,
Would that still be on the same Kelvin scale, or would we need a different scale to, like, when we go down in Kelvin, like degrees, does that change the quantum fluctuations that happen?
it does, but it's weird because what happens, you know, what they'll probably do with this is say negative, you know, just put a minus sign there, -1 Kelvin. But what resulted from that experiment was that the atoms, it flips around. In other words, the energy states of these atoms go negative, which means, weirdly enough, a majority of them become positive. The atoms, when you look at all of them, this is a sampling of all of the atoms you have. When you get that, it ends up being simultaneously the coldest you can get, but because of those energy levels and it flipping around, it's also the hottest you can get at the same time. Um, in that context, anyway.
Yeah, and would what does negative energies, does that always result in positive? What does like negative energy look like when you bring it down in Kelvin?
Well, it's more the statistical population of the atoms. So if you have a bunch of sodium atoms and you bring them down to this level and you're sitting there manipulating the quantum states using lasers and magnetic fields and things like that, you get them even slower than what they would be at zero. Their net energy flips around, so you end up with more positive than negative energies in the individual atoms than you had above Kelvin. And so it just flips around. And it's weird because it becomes energetic again. But that's as far as it goes, because this is brand new stuff that, you know, we don't even know what the implications of it are. Um, so it's a very much an open question, and it's cutting edge research.
Yeah, that's really cool. I also saw you do a whole bunch of you did it. You're constantly doing a series of like new inventions or scientific breakthroughs that we're doing. Like I think you do month by month or something like that, and you come up with like a list of 10. Do you have like a favorite one or a favorite for you that we've discovered recently that you've covered?
Yes, the Wigner crystal. What that is they were able to, and I interviewed the scientists that did this over in Event Horizon, that it had always been hypothesized all the way back to Eugene Wigner 80 years ago that a state of matter made entirely of electrons could be induced and that it would form up into a crystalline structure. It looks like triangles of electrons. And he did it. The scientists, that team did it. They actually created and verified that the Wigner crystal exists, which means you can have a form of matter made up entirely of electrons. And that's my favorite because what's that mean for batteries? What's that mean for all sorts of things? And it's brand new. The hypothesis is real. The Wigner crystal exists. And what if you do it with anti-electrons, positrons, and do the same thing? And that's what they're going to do next. Well, what does a solid crystalline piece of antimatter do?
And what are the real differences between electrons and positrons? What do they differ there?
Charge. One is positively charged, the other is negatively charged. Otherwise, they're identical. But that positive and negative dynamic, if you get them together, they annihilate. But that's all it is just a flipping of the electrical charge.
Where do we find those? Because we find electrons just in just around atoms, or kind of in the atoms, I guess. Where do we find positrons?
Okay, positrons, you need something to flip the electron, and you need, that's how they're created. And there's a bunch of natural processes that actually produce positrons. But the weirdest one is there is a fountain that is stretching tens of light years near the center of the galaxy of something spewing out an enormous amount of positrons, and they're annihilating in space. And we have no explanation for that thing. The positron fountain remains 100% mystery. And we just know that it's there and that there's some mechanism that can make positrons. And you can play with all kinds of ideas. I mean, is it some weird situation between black holes orbiting each other or whatever, doing something? Or is it the mouth of a wormhole? Is it, what is it? But yeah, antimatter there is a mechanism for producing it in nature. And then we can obviously produce it in the lab. We can make anti-hydrogen and all kinds of things. But the problem is that it's quite literally the most expensive substance on Earth when you start making atoms out of it, meaning that it's, you're not going to have a matter-antimatter engine anytime soon.
If we were to make the crystalline structure that you were saying out of electrons, is batteries the thing that we would be using that for, in your opinion?
Yeah, I think that might eventually be one application. But I leave that for the inventors because I'm just superficially saying, well, you're messing with electrons, and being able to keep electrons in one place is storage, So maybe in 50 years' time, this will be the basis of a new generation of extremely efficient batteries. The problem with it is, though, that the material that you have to do that to make the Wigner crystal and get it to do this, you have to sandwich it between two 100% perfect graphene lattices. You can't have any variation. And that's technologically, yeah, we can do it now, but it's not something you're going to do industrially for a long time.
Yeah.
Once you crack that, though, you've got the most powerful or strongest material known. Graphene is amazing, and you can build things like space elevators with it and all sorts of things.
So if we were going to make like an insane battery, we have to get some energy into it. One of the things I really like is we kind of just, what was this, like a year ago? Something like that. We just had the first positive output of energy for nuclear fusion, I believe.
Yeah.
Do you think that is close in like viability for creating energy?
Yes, I think we are. no longer 20 years from fusion. Like people always used to say, we're always 20 years from fusion and we never get there. But I think we passed that. And there's a couple of things that are happening that, really raise an eyebrow. One of them is, you've got governments, ITER, that it's trying to make giant tokamak fusion reactor that would serve as a prototype for a power plant. And then maybe 35 years from now, you could build commercial ones. And they're pretty sure that's going to work. All right. So we could end up with commercial fusion that way. Still decades away, but we've got the experiment running. And that's how we start this. That said, there is an enormous amount of money to be made by cracking fusion energy. And that giant tokamak torus of fusion isn't the only way to do it. And roughly about 10 years ago, it came out that Lockheed Martin was trying to develop a bar fusion method, and that it would produce, a 100 megawatt reactor that's the size of a bus that could be put in cities. It could be launched into space. That project, eventually they said, well, we're done with it. But they never really said much else, that if it worked or not or whatever. And it went dark. And so that may leapfrog everything, and that, all of a sudden we get fusion out of nowhere because some company has been developing it and hits it. I also would expect that the US is not the only one, or the EU, that's looking into creating fusion reactors. China's doing it as well, and they could crack it. So there's any number of white swans or black swans rather that could happen, that deliver fusion into our lab much, much faster than anybody's predicting, overnight, essentially. But that's open. It could happen. If it doesn't,
Why
then, you know.
why is fusion, like when we're cracking fusion, it's supposed to be this like gold mine for energy, but we already have fission, and it seems like we're not using it, and seems like we're not, in at least some regards, it has to be worse than fusion in some ways. Why is that difference there?
Well, the problem with fission is that it produces waste, nuclear waste, and that waste is hard to deal with, although it's possible. The other thing is nuclear accidents have happened, Chernobyl and 3 Mile Island and Fukushima, that have released radioactive materials into the environment. So the concern there is that, nuclear power is not um, all that safe. That said, that led to just a situation where it is enormously expensive to build nuclear power plants. It's just titanically expensive, and that's why no one's doing it. But we're losing the luxury, of, with our fossil fuel situation, we're losing the luxury of being able to choose not to use fission. Okay. Um, so I think you're going to see a new round of fission come along, and maybe smaller reactors built that to where they're fails, that they just can't fail, you know. And that happens with all technologies. Remember, the airplanes, it used to crash all the time in the early days. Planes were crashing and falling out of the sky everywhere. Then you made them better and better and better and improved them, and now they rarely do. They rarely crash, at least commercial ones. So that's what you have to do with fission, is just perfect the reactor in such a way that it can't fail, you know. And
And do you think we'll get fusion early enough to where the amount of fossil fuels we have left and the effect of burning fossil fuels won't be that bad once we start using fusion?
it depends. It depends on the fossil fuel. So by the time we get fusion, say 50 years from now, we will still have a very large supply of coal left. So coal is not an immediate concern. Oil, however, is. And that just really depends on, what happens with, I mean, oil stops being a question if everybody moves to electric cars, which obviously Teslas are becoming popular. or hydrogen fuel cell, or whatever technology you do that gets you off of oil. Um, Other than that, the natural gas is still okay. And you have an alternative to natural gas. You can always go electric, and if you got unlimited cheap electrical energy, well, there you go. But that's those aren't the ones that concern me. The one that really concerns me, as far as running out, is helium. Um, Earth only has a certain amount of helium, and it takes a long, long time to replenish it. And you can only get it out of oil fields because it accumulates in there, and you can recover the helium. Other than that, we have no source for helium. And once it's gone, it's gone, and Earth never had much of it. It's, it's created with radioactive decay, beta decay. And that helium, once it's gone, it's gone. We really need to fill our balloons with something other than helium.
Is that why we're running out? Do we only use them for like making stuff float?
No, because helium is used industrially a lot in manufacturing. And we need that because, helium is kind of an inert gas that you can work in. So helium is, and it's also used, for example, in space as thrusters. That's actually the problem with that capsule that's stuck or was stuck. I don't know. I haven't looked at if they got it out of there yet or not. At the International Space Station is because one of its helium thrusters failed or was behaving abnormally. So we have a lot of uses for helium, which means that we probably shouldn't just be releasing it into the air. That said, we got plenty of hydrogen, and it's lighter than air too. So,
Do you think we could use hydrogen for all the use cases we're using for helium right now instead of helium?
not really. Not really. Um, Hydrogen's problem is that in its gas form, it is flammable in Earth's atmosphere, wildly so. And so, yeah, you could give the kids a helium balloon, but don't get the matches around it. But it will do it. And hydrogen is a good lifting gas. It's excellent, and it will and again, you can get hydrogen from water. Break up a water molecule, and there you go. So the hydrogen can, but the helium is completely inert and it's not dangerous. So it isn't flammable. And that's its real virtue. But the funny thing about it is that helium is actually a worse lifting gas than hydrogen is. But again, with hydrogen, you end up with a Hindenburg. You build a Zeppelin out of this thing, it's explosive. And that's what happened with that Zeppelin, and a number of other ones. They burn. But can you manage it better and make better containment of the hydrogen and limit the explosive, ability structurally? Yeah. So that's how it's going. But yeah, hydrogen, if we need to lift stuff, hydrogen will get us by just fine.
So we're using a bunch of helium industrially, like you said, but we're running out of it. Is there a way besides besides hydrogen? Did I say hydrogen to start? Is there a way besides helium, or is there a way besides hydrogen to use instead of helium for our use cases?
It depends. Depends on what you're doing with it. If you need it to be inert, yeah, you've got a couple other inert gases to choose from that are actually even rarer usually than helium is. But in processes that like a thruster and on a spacecraft, yeah, there are other ways you can do that. You just do hydrazine or anything like that, compressed air even to some extent. So yes, helium is replaceable in some things, but not others, and that's going to be the big problem because helium escapes. It escapes, and once it escapes, it heads up and gets blown by the solar wind off into the solar system. So,
Is there a reason we're using hydrogen instead of other things for our use cases that aren't like, let's say, just like helium balloons? Is there a reason we are using helium instead of other things?
yeah, well, helium was easy and cheap because it was coming out of the oil wells. Um, so that's really why why it became prevalent. Um, and it's incredibly useful. Helium is extremely useful, and it is a lifting gas, and it's also just so inert. It doesn't react with much of anything. So so that's why it was useful. Whereas hydrogen is very reactive, and it reacts with oxygen, and that's bad news. That's explosions, and that's another reason why helium is that it's a fairly good alternative to hydrogen. Um, so there's that. The other thing is that I think we're going to have technologically. I think blimps are going to make a comeback, Zeppelins, because you know a helium Zeppelin has a lot of, if it's big, it's got a lot of lifting power, and there's companies out there talking about creating them so you can move lumber, from logging camps with Zeppelins. They're talking about solar powered Zeppelins that can, basically cruise ships in the sky. So there's all kinds of ideas about bringing back the Zeppelin, and literally the company Zeppelin has been reconstituted, so you can actually go and buy a Zeppelin from Zeppelin. So I think that's going to be a thing in the future. The thing is it's using helium, a lot of it.
Yeah, I think the reason we're using helium is just because of prices. I feel like that's what drives a lot of our economy, is just like, oh, it's cheaper. Let's use that for practically everything.
It's true. It's cheaper until it no longer is, and that's how it'll go with helium. Is it'll just get increasingly expensive as it gets scarcer until it's no longer. It's just too expensive to use, and that's how it'll go. Same with oil. The price of oil will just rise as it gets more scarce until it's no longer economical to use it as a means of transportation, and that's imagine if gasoline was 10 times more expensive than it is now. People aren't going to be going to the McDonald's on a whim, at midnight. So it works that way for any of these commodities that that we're talking about. Is that the scarcer they are, the more expensive they get, and you have to find an alternative. And that's why I think, probably the future for oil and cars is electric.
Mm-hmm. All right. Thank you so much for coming on. I don't think I have any more questions. What's the name of your book, and then where can people find you?
The name of my books are The Salvagers and Supermind. Supermind being the most recent, and then I've got another one in the works that'll be out next year. And to see my YouTube channel, just search my name, John Michael Godier, Godier, and you'll see that. And then also I host Event Horizon, which is a science-based and science fiction-based podcast each week on Thursdays, all on YouTube.
All of John's stuff is going to be linked down below, so make sure you check out his podcast, his YouTube channel, and his books. And click this video right here to hear my conversation with another guy about some science stuff. That was a fun conversation, so make sure you click it before it disappears. Wait, I'm not actually sure if these things disappear. Did the end cards disappear? I don't know, but click it anyways. Go ahead. Click it.